retrofit and strengthen our load path. Then enhancing changes in use and alteration. We change the building use from commercial to residential to commercial. We need to upgrade all the columns and beams to take that additional loading. There may be corrections to be done because the detailing was done wrong, the design was insufficient, wrong at start, or at construction time they forgot to put in some reinforcement, or the thickness of the slabs were not sufficient, and errors like that. Increasing resistance to seismic effects, improving service life and durability, and structural upgrading to comply with current standards. So you see here a photograph which shows you in a nutshell the use of these laminates and fabrics. So carbon fiber comes as thin laminates, only this wide, 100 millimeters wide typically, 1.4 to 3 to 5 mm thick. They're not very thick, 5 mm. I'm talking about maximum 5 mm. And it also comes in the form of fabric, which is a weave and weft, either one directional or two directional strengthening. And these fibers are extremely strong, 3,200 MPa, 2,800 MPa, and things like that. So they're very, very strong material, comparable to even beyond steel. And they're very lightweight, extremely lightweight, and they can be used to retrofit masonry structures like you see here. They can be even pre-stressed. These little laminates can be even pre-stressed. They're simply glued onto the surface with epoxy. Okay, in a nutshell, they're laminates, and they're glued onto the surface, they bond with the surface, and they give additional enhancement to strength. So you can use it for masonry strengthening. You can strengthen cutouts where insufficient detailing of reinforcement has been done and stress concentration. You can increase, say there's a lift shaft, you can strengthen it on the lift shaft. You can strengthen the walls, concrete walls. You can strengthen in shear where there's lack of stirrups. You can add the stirrups externally. You can add laminates and glue them at the bottom to increase the flexural strength of this beam. You can strengthen the two-way slab, one-way slab. You can strengthen it. You can strengthen by wrapping with the fabric. Wrap the fabric in the form of a U. You can wrap the fabric and enhance not only the flexural but also the shear resistance. You can use these fiber anchors below these fabrics so that they spread and they provide good bond. And you see here the various types of fabrics that can be used. You see here on this floor and on this floor, the wrapping of the column to enhance plastic capacity, ductility, and even increase the axial capacity of these columns for increased loading. You can strengthen floors above, for example, you can strengthen the masonry wall with wrapping. So this is a wonder material which adds almost insignificant weight to existing foundations, and there is no impact on foundations thereof. And we can simply strengthen. Earlier, we would be doing concrete jacketing, heavy, extra weight on foundations. We would be doing steel jacketing, corrosion and other issues, and heavy weight. And now we are simply able to wrap these with extremely light. You can carry it in hand. They come in rolls. They're a simple fabric. They come in fabric form or laminate form, and you can wrap them. You can wrap them here. You can add laminates at the bottom. Just glue them with epoxy. So this is the concept of strengthening, which adds no weight to the foundation, and you can selectively enhance flexural, shear, axial, ductility. You can, all combinations of those also. So this is a wonder material properly used. And here you see a typical use of a company called Sika, which were pioneers in this development of this product for commercial use. You see the flexural strengthening here, the demand here, and negative side on top of this slab because of the bending moment. Here you see the use of fabrics to increase shear resistance, and of course they are replacing the stirrups externally. Insufficient, or the shear demand has gone up due to the European lorry, for example. In Europe, the shear demand went up, shear failure becomes important. When you strengthen in bending, of course you must strengthen in shear because one is a differential of the other, of course. So you can also enhance by increasing the seismic capacity. Chennai went up from seismic zone 2 to seismic zone 3 in the last code. So a number of elevated structures were vulnerable, and this is a quick, rapid, easy, lightweight mean, no heavy equipment, extremely sustainable. So the biggest argument for this, I would argue, is the weight and the sustainability argument. You're using carbon. You're using carbon after all. So here you go, you can see, you can strengthen the slabs of the bridge decks, you can strengthen the beams in flexure, you can add the external stirrups, and you can see these are actual projects in which it is done. How I came into this? About 15 years ago, I was asked by a company to strengthen, this bridge, which is on National Highway 1, the most important national highway, and it is near a place called Cheru at Pagwara, Cheru Bridge at Pagwara on the Panipat Jalandhar. And this is a strategic road because there are tanks and army vehicles flying all the time. So what was happening was this was built to a class of 45-hour loading, and our tanks and heavy army vehicles are 70-hour and beyond. So we needed to retrofit this. They could not decommission this bridge whilst the other one was being built parallelly, the 4-lane. So this 2 lanes was to be strengthened immediately whilst the new 4-lane would be added adjacent. So this was the demand that came to us, and we were told for this structure, which is 27 meter span, 7.5 meter, 2-lane carriageway, to upgrade the bridge, okay? And it was pretty old. So this was the condition. We had spalling, we had a number of pre-stress loss. We were thinking about 15-20% pre-stress loss, a lot of spalls, and there was also cross pre-stress diaphragms and cross pre-stressing of the deck, and all these short pre-stresses had gone completely with time. They were aged and they were gone and they'd lost their pre-stressing. The ability of the bridge deck, which depends on pre-stressing, was seriously hampered. So there was a double whammy: A, upgrade; B, the loss of pre-stress and the bond that the damage to concrete which has to be made up. Typically, you see vertical cracks, and you know that pre-stress has been lost. They are typically, the loss of pre-stress manifests itself like this, and you see in the bottom bulb and you see in the web walls also this pre-stressing that's happened. It's a telltale that something is wrong, right? And what we do is we always sandblast this deck. You see the cracks and crack patterns only after you sandblast. You see much more clearly the cracks and crack patterns after you sandblast because there's so much accumulated dust and mud and deposit on that. And then you see how clear you see these cracks. You don't see it here. You see how clearly you see it here when you sandblast, okay? So this is something most people avoid, but this is something which should be done. And we open up all these cracks, then we will grout those cracks, we will repair like normal repair, we will epoxy repair, grout those cracks, complete those cracks and densify those cracks with this grout, make them integral with the bridge. Typically, grouting is done from bottom to top, as you know. You start with the lowest nipple and it comes out from the top, then you close this fellow and it comes out from the top. It's anti-gravity. You always grout against gravity. And then you grind down the surface, make it smooth because something has to stick. It has to be an even surface. You grind down all unevenness. Then you mark where the laminates will go. You mark them so that you know it will go in that line. Then if it is to be buried, we have something called a grooving tool. And up to about 2-3 millimeters, we can cut into the concrete with this grooving tool and bury the laminate just few millimeters into the concrete. So you get adhesion bond from the epoxy on 3 sides. And it gives enhanced resistance from debonding. Debonding of these laminates and wraps are the basic failure mode. One of the most important failure modes to guard against is delamination of the laminate as well as the fabric, and how to do it and how to deal with it. So once we have done that, we make even the surface, then we put in the end laminates where we need to anchor them in mechanical anchors so that it's held up and doesn't debond at that bond length point at the end. And if we have 2 directional, then we groove in one direction so that it's buried, and in the perpendicular direction we simply paste it on. So when 2 laminates cross, one is always NSM, that is near surface mounted, buried, grooved in and buried, and pasted, epoxied, and the other one is pasted on top. So you see these 2 both perpendicular and in the long direction. Not very heavy equipment required at all, no fancy equipment, no lorries, no nothing, no major jacks, no hydraulics, no huge energy requirements at all. Huge sustainability arguments for this. And you can see how easily simple people are able to just paste this. It comes in the form of a roll. You just keep it on your shoulder and wet it and epoxy application and put it up, okay? You can cut it easily with a tool. You can just put it with laminate. You put the epoxy there and then you take it up and just paste it. Okay, it is so simple as this. and it adds strength tremendously to the structure. It increases flexural, axial resistance as you require. Here you see a mechanical jack which has been specially developed, and this jack is used to pull this strand and give it 5 to tons pre-stressing. Now, why do we pre-stress that? So that it becomes active the minute the live load comes. It is already under tension, it will get mobilized immediately. If you simply glue something on this laminate, it's a passive laminate. This is an active laminate when it's pre-stressed. If the passive laminates are pasted without this pre-stressing, they do not get mobilized until you get sufficient deflection. Okay, so that is the difference. So we always try and pre-stress some laminates and give passive some other laminates, as we have done on this bridge, where we added 3 laminates, as I'll show you. Now here you see the surface, the wrap being added. You can see this black mesh, and how with a simple roller you apply the epoxy and roll it out. Here we have what we call hold-up wraps to prevent the laminate from debonding along its length. We have hold-up wraps along the length of the girder, the bottom bulb of the eye girder. Here you see the fabric wrapping of 600 GSM being pasted, and what it looks like, it's simply a thin fabric pasted onto the, you see here now how we've strengthened the diaphragms, the members, you see here all the cutouts which are there, you see all this strengthened, and you see here now how fully retrofitted girder. This was a 5-span or 6-span girder arrangement, and as I said, we had also lost the cross pre-stressing across the deck at various locations. So with very lightweight equipment, without stopping traffic, we were able to complete the repairs of this upgrading of this bridge. Now when you strengthen the bottom of a bridge, everybody knows bending moment and resistance. You know, you have something called Z, I by Y. So you need to strengthen the top also. You can't simply strengthen the bottom, otherwise the section behavior will completely change. So we raked out the entire deck, we removed some surface of the concrete itself, and we put in a membrane of M60, 60 millimeter thick M60 grade concrete at the top as a compensation for this loss of pre-stress. You can see they were absolutely useless pre-stress, and they had gone over the years. All this cross pre-stressing had gone, including at these diaphragm locations, and we made up for that by putting this at the top, also balancing the flexural I by Y, the Z requirement, C equal to T nonsense and all that you know about. And here you see the finished deck, and the load testing was done. It was operated at 70R, and it was held, and the whole testing procedure is carried out as per RC with 98% elastic recovery in the elastic limit. And here you see the completed bridge. Traffic is plying. Traffic was never stopped when this bridge was repaired. The most important point, traffic was never stopped when the bridge was repaired, except at the points in time when we needed laminate to bond without putting live load, which was done mostly in the night. Okay, so you see here the various stages of repair. Here you see the staging. Here you see something which is yet to be repaired, starting from that side, progressively how it happens. Here you see a finished. Here you see partially, you see the shear wraps at the end making up shear. And at the bottom, those laminates have been pasted on each of those girders. And you can see you don't need any sophisticated high-tech work or high-tech tool, but very high quality assurance, the quality of the materials that you use, the product that you use. So the lessons learned. Now, I did this 15, 20 years back. Many bridges were built, were strengthened willy-nilly all over India without any guideline, following the ACI 440 guideline to some extent, and without any workmanship rules, without any proper design guidelines. And here we had to, develop a design guideline. There was a need, and we knew that it is useful. It was proven that it is useful, so we need to develop a guideline for India, which I later got charged with as a convener, and myself and Surya Prakash developed these guidelines along with the whole team. We developed these guidelines which have been approved for the first time in India. We have a guideline for the use of CFRP laminates and wraps for strengthening. So there are many needs for this guideline to ensure safety, quality and performance, because willy-nilly use was going on without any regulatory guideline for the same. We avoid unregulated and inconsistent practices. We need to provide a legal and technical framework for practitioners, because if something fails, things become legal, and this guideline will then provide a basis for conformance, acceptance, etc. So challenges without the guideline: if we don't have a guideline, misuse of materials and long application techniques, lack of design and consistent quality assurance, incompatibility with local environment conditions. International guidelines were referred. We biased ourselves on the FIB 90 for design because it follows limit state design. The ACI 440 does not follow limit state design. It follows LRFT, which is slightly different, and it uses a different format and framework for the resistance side. apart from the loading side. So we chose to go with this new bulletin FIB 90, which it came out, borrowed largely from it, the technical guidelines of the Concrete Society UK, and of course the American AASHTO guidelines, which came out as we were about to produce our own guideline. In India, we had no reference except a passing reference in SP 40 in this guideline on repair and strengthening that you can use FRP or CFRP for strengthening bridges, one line. But how to do, what quality of material, what conformance, nothing was given. So over a number of meetings held at IIT, Hyderabad, VJTI, at my office, at other offices, we met many, many times, and you can see we were in the lab. There's a unique testing machine that was developed for testing the toe, and we developed these guidelines from 22 till late 22 till last year, late last year, where it was released by IRC. The many meetings that we had, and here you can see some of the strengthened cylinders that were tested, and wrapped columns that were tested, etc., and some of the specimens at the lab. Here you see the machine for testing the toe, 24K, 12K toes that were to be tested to verify the quality of the laminate, the carbon fiber that you're getting. So we met many a times to meet this guideline, and the guideline has an introduction with the need and the different types. It has a scope, and then it goes on to discuss what are the strengthening systems. Those are cured systems, wet layup systems, and the fiber anchors, as I told you. Then we have hybrid systems in which you can use ultra-high performance concrete and normal CFRP wrap, or you can use laminates and wraps in a certain way in a hybrid format. And then, of course, there's the issue of fire. Epoxy catches fire easily, how to delay fires. Then, of course, there's the matter of ultraviolet radiation, this exposed sunlight, and UV epoxy breaks down under sunlight. So we need to be sure that it doesn't, and how do we guard against that? All this is discussed in this code. Then when we use it in conjunction with other strengthening systems, what about the requirements for carbon fiber, carbon fiber fabric, and the epoxy? What are the requirements, material, conformance requirements, their testing, their acceptance? How do we test these things to know that they're good enough to use? There's no, what is the level of variation we can accept, etc. So the test procedures have been developed and stated in this document. Analysis and design complete, dealing with shear, dealing with bending, dealing with ductility. For the first time, we give comprehensive guidelines, including our own load combinations of IRC, and in keeping with the limit state method, ULS, SLS, rather than the American LRFD method. So we have developed for flexural limit states, we have developed for serviceability limit states, tracking and deflection, fatigue, and then we have developed the guideline for combined axial force and flexure, what guidance in columns. And then similarly, we have shear and torsion effects, how we deal with shear and torsion in design. And then the seismic strengthening aspect, seismic upgradation. The code 1893 is going to create a whole new area of business for these people, because there's going to be so many areas of structures, especially strategic locations, which are now entire Northeast is in seismic zone 3, means all of Assam, all of Northeast is in seismic zone 3. You can imagine what that means in terms of seismic upgradation. So similarly, you have here quality control. For the first time, what are the quality control requirements? What are the testing requirements? What should be the acceptance criteria? At site, once we've installed, what should be the test procedures that we need to do? If something doesn't conform at site, how to set it right with a patch? All this has been developed in this, apart from giving an annexure of worked examples, 6-7 worked examples demonstrating all the equations used, and then case studies, 6 or 7 case studies of practical actually used in structures. So Surya, can I call on you to take over from here? So I want to tell you before Surya reaches that this would not have been possible without Surya and his team. I don't know if other members of your team are here. Can you ask them to stand up? Can you please ask them to stand? So these are all the gentlemen you see, maybe ladies also, I can't see in this glare, but these are the stalwarts who have worked under him, and a lot of Make in India research is in this guideline.